Hi, this is Barrett Givens from the Math and Stats Department at Cal Poly Pomona, and right now we're in a pretty historic time. It's certainly unlike anything I've ever experienced before. There's a lot of talk about social distancing and the coronavirus, and I realized that there's a really classical, famous problem in combinatorics that might be relevant right now in the time of social distancing. So I thought that maybe we might enjoy this fun video to learn about a fun math topic in the context of social distancing. So the idea is that let's say we have a row of computer desks, and because of social distancing, we don't want students to sit at two desks that are directly next to each other. So we want people to avoid sitting directly next to each other. And then the question becomes, okay, well, if we want to have that happen, then in how many ways can a row of computer desks be occupied by any number of students if the students are following safe social distancing? So you can sort of imagine, you might have like 10 desks and then like 2 or 3 students, and they can be arranged in all kinds of different ways, but just the only rule is that they cannot be directly next to each other. And the question is asking, so how many ways can that happen? How many different ways could they choose to sit down, and as long as they're still following the rules? This kind of combinatorics problem is often solved by starting with a small value of n. So I'll let n stand for the number of desks, and let's start with n equals 3. So I've got my 3 desks, and then I can think about, well, if there's just one student, that one student could sit at the first desk, at the second desk, or at the third desk. And I'll show this with these diagrams where student sitting at the first desk is designated as XOO, second desk OXO, and so on. So the X is where the student is sitting, and the O is where the desk is empty. Now, what about if there are 2 students? Well, if there are 2 students at these desks, this is the only way it can happen, is XOX. What if there are 3 students trying to sit at these 3 desks? Well, it's pretty clear that is just not possible. We can't have 3 students sitting at 3 desks and still have social distancing. The one case that you might not be thinking about, but is a possibility, is what if we have no students in the room? That's still safe by the rules of social distancing, right? And so we should make sure to also count that one, 0 students. Okay, so these are all the different ways, with X's showing where the students are sitting, where we could have social distancing at a row of 3 computers. So let's go ahead and count them. There's 3 ways, 1 way there, and 1 way there. When we add them all up, we get 5 ways. So if there are 3 desks, there's 5 ways to organize the students. Okay, let's try n equals 4, and we'll do the same kind of analysis. We'll start with 0 students, then 1 student. The student could sit in the first, second, third, or fourth desk. And then we'll think about 2 students and how they could be arranged. And so they could be first and third, first and fourth, second and fourth. And I think if you think about it a little bit, you can convince yourself that these are the only choices, and that if there were 3 students, we couldn't have social distancing. We'd have to have some 2 of them next to each other. So this is it for n equals 4 desks. So we'll go ahead and count the list. And there's 8 in that list. So when n is 4, the answer is 8. Okay, let's do it one more time with n equals 5. With 1 student, and then with 2 students, we get all these different ways. And finally, if we have 3 students, we can do that, and that's the most we can have. So let's count all these up. 1, 2, 3, 4, all the way up to 13 different ways. So far so good, but now I think you can see it's kind of blowing up. So if I tried to do it for 6 desks and I just tried to list them all out, I think I could still do it. 7 maybe I could do, but we're pretty quickly getting to the point where it's just like too many to just count in a list like this. So we need to figure out like a trick to it or a pattern. We need to sort of figure out another way to organize this information so that we can see a pattern, and then we can figure out in general what the number is. So I want to look at this list for n equals 5, and I want to look at it again, but arrange it in a slightly different way. So I'm going to write down the same list, but I'm going to write it down in a little bit of a different order. So I'm going to start with the ones with just one student. But then the last one with just one student, I'm going to just write it over here on the side in purple. Now I'm going to look at the ones with two students. So I'm going to do it like so. And some of these ones with two students, I'm going to write over on the side. And then also the one with three students, I'm going to write over there on the side in purple. Okay, so why have I put some on the left and some on the right? You could maybe think about it for a minute. Let's count how many are in each section. So on the left in black, there's 8 in this column. And then on the right in purple, there's 5 in this column. So I really did get all 13 from the previous page, but I've split them up into 8 of them and 5 of them. 8 and 5 is 13, which is what I got before. Now, how did I divide them up? What's different between the left column and the right column? And the clue is to look at the last desk. So in that last desk, on the left, the last desk is all empty. So in that column there on the left, where the last desk is all empty, really it's almost as if that desk could have just not even been there, right? And that list right there, if you only look at the first 4 numbers, 0, 0, 0, 0, x 0, 0, 0, that's the same list from the previous page for 4 desks. And so that 8, that comes from the answer for n equals 4. Okay, now what about the purple list? You might actually have a hint that the fact that the number is 5, and we saw the number 5 once before in this video. So on this one, they all end in x. But even more than that, if it ends with x, if the 5th desk has a student in it, then what does the 4th desk have to look like? If the 5th desk has a student, could the 4th desk also have a student? No, right? They can't sit next to each other. So if it ends with x, then right before the x must be an O. And so all of these in this list end in OX. And then if you just look at the first 3, OOO, XOO, OXO, OOX, XOX, those are the same 5 that we found when n equals 3. So that 5 comes from being the answer for when n equals 3 desks. And so we take those two numbers, we add them together, and we get the number for when n is 5. So let's just make a chart now and kind of think about what this is going to do. So I'll have the number of desks on the left, the number of ways to practice social distancing on the right. When n is 3, we got 5. When n was 4, we found that there were 8 ways. When we had 5 desks, we found that they were 13 ways, and we saw that the 13 could also be found by just adding 8 and 5. Well, so then when n equals 6, I think we can do the same kind of reasoning. When n is 6, we could list out all of the different ways when n is 6, and we could take the ones that end with an O, and then the ones that end with an X, and we'd see that the ones that end with an O, there would be 13 of them, because they would be the same ones from 5 desks. And when it ends with an X, then that means it ends with an OX. And so I can just add 8 and 13, and I'll see that when there are 6 desks, there are 21 ways. And when there are 7 desks, there's 34 ways, which I get from adding 13 and 21, and so on. So those of you who are in the know here are maybe recognizing what is this really famous sequence of numbers that you get by starting with some values, and then every time to get the next value, you just add the previous 2, and that is the famous Fibonacci numbers. So, the number of ways that you can have safe social distancing at a row of computer desks is the n plus first Fibonacci number, which is kind of surprising and really cool. So this is a famous problem in mathematics. Maybe it's not been phrased before in terms of social distancing, but as I was thinking about social distancing and thinking about all of the things we're doing right now to keep ourselves safe, I remembered this problem and I thought it would be a fun thing to share with you.